Don't, please. That's ridiculous. Don't be ridiculous. Okay. Have you got that? Yeah?
No.
Please, this serious business here. Serious business. Transformers. Okay. Right. So, in this lecture, we will study Transformers. So, this, for example, is Optimus Prime. Okay. You know his enemy is Megatron. Yes, we all know this, don't we?
No, Megatron and Optimus.
Yeah, no. Yeah, sorry. That's not, I'm afraid it's not as exciting as the movies. This is what a Transformer looks like.
It's so beautiful.
It's an iron core with wires wrapped around the ends.
Oh my god. Do you have to draw that?
You do. Now, just before you draw that, let me just explain the different parts here, okay? So, what you've got a piece of iron, usually. And here we have a wire wrapped around it. And we call this the primary side. So this is the primary voltage, the primary current, the primary number of turns. This side is called the secondary side. This is the secondary voltage, the secondary current, and the secondary number of turns. Okay? This is what a transformer looks like. They're very, very simple machines. But they're actually very useful because we can, in a moment, we'll see what we can use them for. But first, I want you to draw this. You might have to draw it in the exam. Yeah, I'm afraid so. Artist class. That's what biology is. Are you speaking English or sandwich?
So the primary coil must more than.
Not necessarily. It could be more or less. In this picture, it was more.
Also, it must more and less or more and less.
Yeah, what you cannot have is the same.
Well, no.
It's useless, yeah. It'll be useless. Yeah, we'll see in a moment. They must be different number of turns.
I'm so good at it.
Oh, come on, it's not so bad. It's just a square.
It's 3D. Not that. Square is 2D.
Well, excuse me. It is what shape then? I simply use square because I know you know this word. Do you know the name for this shape?
Square. Rectangle.
Cube. Transformer.
Yeah, exactly.
It's a transformer square.
Why?
No.
I believe the shape of the transformer.
It's going to be some kind of shape like a punctured cuboid or cuboid torus.
Square.
A rectangular torus, perhaps. I don't know.
Hello.
Hollow, yeah, no, hollow.
Yeah, hollow coffee.
Hollow cuboid, yes.
Cuboid.
Yes, correct. Yes. Yes.
Laugh.
Why are you laughing? He's right. That's what it's called. No, not a hello cuboid. A hollow cuboid. Or hollow. You can pronounce it both ways.
Hello.
How do you say it?
Hello.
Hollow.
What do you say?
Hollow.
I wouldn't say hollow or hello anyways, I would say punctured. Yeah, donut. Okay, continue.
So the red one is primary.
Primary and the blue one secondary. What?
What?
I don't know what her problem is.
Yeah, her problem.
Yeah.
No, her problem.
Her problem.
Because
You're
it's
right.
our PM.
You're right. You're absolutely right. I don't know what's wrong with Monica. She's losing her mind. What's so funny? I really don't understand. No. Alright, continuing. Now, what's really important to note is that this transformer only works if you're using AC. AC is only working.
Oh, yeah.
Alternating current. The current that changes direction. Now, think about the logic here. According to the right-hand grip rule, we have a magnetic field. Right? Yep. If we have AC, what's happening to the magnetic field? It changes. It's going like this, right? Now, if we have a change in magnetic field and there's a conductor nearby, what will happen in the conductor?
Plus minus.
Yeah, well, what will we get? Yeah, from Faraday's law. So, keep the order in your head here, okay? Look, here we have no current provided. Here we provide a current, but the current alternates. According to the right-hand rule, we get a magnetic field. But because it's alternating, the magnetic field is changing. Because the magnetic field is changing, then we get a current here in this conductor. But let's see what voltage we get, okay? So, Faraday said that the voltage, we'll call this voltage here V2. That should equal, and we won't worry about the minus, okay? That should equal N1 change over time. Now, why am I saying N1 and not N2? Because the current we get here is caused by this winding. That the magnetic field around this one causes it to appear here. Okay. But likewise, you could look at the picture the other way. When the current is running here, it will produce a magnetic field which changes, and by the same logic, we could have stuff happening on this side. So equally, we could say V1 equals N2 over that. Now, this does not change. This is the same for both, because it's symmetric. The time obviously doesn't change, and in this one here, what's actually changing, the B or the A? The B.
The B.
Because the A is all these circles, it doesn't change, okay? If I divide these, no, I've made a mistake. I have my 1s and 2s mixed up. Yeah, sorry, apologies. I should have 1 and 2 here, shouldn't I?
No. Yeah.
Wait. Was I right the first time?
You just bring N over.
This is wrong.
They have the same flux over time. The only difference is the number of
I feel like my 1 and 2s are backwards.
I feel like you just pull over the N1. And then V2 over N1 is equal to V1 over N2.
Yeah, but the problem is I know what answer I'm supposed to get.
Oh.
This is the problem. I think I wrote this backwards. Let me just picture here. If I call this V1, and this one I call V2, and the V2 is because I'm so sorry. I know what I said wrong here. In this picture here, this makes a magnetic field, and this makes a magnetic field. So the magnetic field here goes with the N2, and the magnetic field here goes with the N1. I have it the wrong way. I should have said V1 equals N1 this. And I should have said V2 equals N2 this, is what I should have said. That's what I should have said. Because now if I divide this, I get V1 over V2 equals N1 over N2. That was the result here. What I was looking to get. This is the formula for the transformer. It can tell us the relationship between the voltages if we know the relationship between the number of turns. Of course it's this. What was I thinking? I totally forgot what I was doing. In Faraday's law, when you have a magnetic field around the conductor, it's how many turns around the conductor that you care about. Not about the other side. Yes, I totally had that backwards in my head. Okay, is that okay now? Yeah. Continue? What? Okay, continue? Yeah. So a transformer, what is the purpose of it? It's an electrical device, and it's used to transfer electrical energy between two circuits through induction. But the key thing here is that the induction, okay, this is a lot here. This is explaining what a transformer, how it works. Why do we want it? The reason is transformers are used to increase or decrease voltages. What I need you to do, you can write the whole thing, but for the exam, what is the purpose of a transformer? It's the last sentence. Transformers are used to increase or decrease voltage. For example, if the N1 is bigger than the N2, then this equation tells us the V1 should be bigger than the V2. Or likewise, if the N2 is bigger than the N1, then the V2 is bigger than the V1. So in other words, if I look back at my picture, if I want to make my voltage here bigger than the voltage here, should I have more or less turns? More. And in this picture, what is happening? Less. So it will take an input voltage and produce an output voltage which will be less than the input voltage. Okay, so can you write down just the last sentence? Transformers are used to increase or decrease voltages of alternating current. Now it only works if it's alternating current. It doesn't work for direct current. The last sentence at least. Yep. Yes. Well, the reason we need alternating is because we need a change in magnetic field to induce the current in the neighbouring coil. That's why DC won't work. Now, you could kind of get it to work with DC, but you would have to do something like flick the current on and off quickly to produce a change in magnetic field. This is the only way I can think of getting a DC current to work to change its voltage. The power companies, they use the transformers to change the voltage. So you notice in your home, what's the voltage here? 240 about. But the power cables outside, the big power cables, they're not 240 volts. Does anyone know what they are? Yep, 10 kilovolts, 10,000 volts. Does anybody know why the power cables are at such a high voltage?
Lower the resistance.
It makes it more efficient.
Can decrease less energy.
No, because we'll get to that in a moment. We don't actually change the energy, only the voltage, and we'll see what happens now. Bruce was asking me, can we decrease or increase the energy? Not quite. Does anyone remember what the power formula is? Power equals... Yeah, but when we're talking about electricity. VI, okay? Conservation of energy says the energy at the start equals the energy at the end. So that means the power in should equal the power out. If the voltage increases, then the current decreases to keep the power the same, and vice versa. These transformers are actually in your home quite a lot. Like here. This here will take 220 volts and convert it into something quite small, like 19.5. So this is a transformer. Takes the 220 AC and converts it into 19.5 AC.
What if there is one?
Yeah, these boxes, they're actually two transformers. I think you can switch between the two. So it can actually take 100 or 240, it says on it. And it can also take 50 or 60 hertz of alternating current, yeah?
Is there a transformer in the adapter?
Yeah, now, back in the day, the transformer used to be like my picture, an iron core with the wires wrapped around it. I feel like they're more advanced now, because when you look at like the transformer on your phone plug, like when I was in high school, the plug for my mobile phone was always something quite big block. But now if you look at a charger plug, it's quite small. So they use a very advanced circuit and electronics to change the voltage. They don't rely on the transformer that I have in my picture anymore. Now I think for very large jobs, like at the power plant, when you have something like 10,000 volts, it's better and safer to use the diagram that I have. But for something like your phone that goes into the wall, I think nowadays, am I right in thinking that the charger looks like just a normal plug? Whereas the older plugs were quite big, like a big block. If you broke this open, you would see the transformer inside of it. Yep. So we have two types of transformers: a step-up transformer. What do you think a step-up transformer might do? Increase voltage. And so the other one, what to do? Yeah. So please, step up, step down. You should know those words. So what do I need for my laptop? What type?
Step down.
Step down. Yeah. Is there anything in your home that needs a step-up transformer?
Air conditioner. Air condition.
No.
Refrigerator.
No.
Heater.
No. Nothing needs a step-up transformer in your home.
Television.
No. Nothing.
Converter.
Everything's a step down. The only...
Adapter.
No, everything's step down in the home. Step down, yeah. Or no change.
Phone charger.
It's all step down.
Because if we go to 110 volt country, it's step up.
No, okay, I suppose, yeah, okay. So if we were living, if you were coming from a country of 110 and moving to a country of 220, then you would need a step-up transformer to increase from 110 to 220 or whatever. Yeah. But most countries are the 220, aren't they? 240? 220, 240? Yeah.
Why all contracts different purchase? Like
Yeah,
110 and 220 and here 230 and
Because
It's so inconvenient.
and you can skip the rate.
oh, it's not exactly the same. What's it in Kenya? That's here, 240. And what's it in Malaysia?
240.
240.
USA 110.
Taiwan's 120.
Yeah, because
Then I
they
find
Korea?
220.
220, not 240.
yeah, it's 220.
But 220 and 240 is okay to use.
It is, yeah.
No more than 6,
Huh?
380
No, it's not about safety. This is important. 110 or 220, there's no safety difference. The difference was, the reason we have 110 is because about 100 years ago in America, when they first had electricity in their homes, people weren't so sure about if it was safe to have in their home. So for advertisement, they said, okay, we will change the voltage from 220 to 110 to make people feel safer, because in their head it goes from a big number to a small number. Now in real life it is just as safe and dangerous, 110 and 220. It's the same. But people felt, because the number is half the size, it's twice as safe. Yeah, but if you stick your hand in 110 or 220, you're just as dead. Yeah. You're dead.
But you have that.
No.
Some people can
You
conduct
could-
electricity.
Everybody can conduct electricity.
With into the contact, you can start.
Yeah.
Huh?
That's the premise.
Yeah. You have to be very careful now. If a battery was like designed to be 6 volts and you charge it up using 12 volts, then you can damage the battery. So you might charge it up quicker, but you will damage it. Yeah. So just, do be careful about that.
What if we need 12 volt and we charge with 6 volt? Will that damage them?
If you what?
If we need 12 volt but we charge with 6 volt?
Yeah, usually undercharging is not going to damage it. It'll just make it a longer process. Yeah, it's overcharging that a higher voltage can damage the electronics. Okay, so we have this formula. Now, since Bruce was saying about the energy, if it's 100% efficient, we can state power in must equal power out. Now you realize if I say power in equals power out, that means I1 V1 equals I2 V2, which means I1 over I2 equals, oh sorry, I wrote it the wrong way around. I wanted V1 over V2 equals I2 over I1. But what does V1 over V2 equal? N1 over N2. So you could also say N1 over N2 equals I2 over I1. So we can make this formula. Please note the opposite relationship to the voltage. Okay? Yeah. Hey, you want to go back to this, is it? Yeah? Okay. Continue? Yeah? So we have this formula? Yeah. Right. Here's a little example for you to try. A small toy requires 6 volts. but it gets power from a 220 volt AC supply. The number of turns on the primary is 4,400. Tell me how many turns there are on the secondary. Okay, calculate that. Should be a easy enough calculation. So is it more or less turns? Less, because it's a step down transformer.
$120.
120 turns? Yeah. Yeah. $120, it's because 220 over 6 should equal 4400 over N2. Didn't you try it down, Jerry? We should have V2 over V1 equals N2 over N1. So N2 is, what did you say, Bruce?
And 120.
120. I have it the wrong way?
Yeah.
Oh, sorry. This is V1 over V2 equals N1 over N2.
Yeah.
N2 is 120. Is that okay, Jeremy, or not okay? It's okay, are you sure?
Yeah, okay,
Okay. Continue. So, let's have a look at the questions here.
This homework.
Listen, this is a great question in the exam because it's just so straightforward. Can you try these for 5 minutes? In fact, I think you should get these done in 5 minutes.
I see the question just in 5 minutes.
5 minutes, I'm finished, I think.
Oh,
Try it.
okay.
Monica, leave Jerry alone. Jerry, take the picture. Monica, please. Jerry's trying to do his homework.
Yeah, don't stop.
Is there?
Don't give me reason to do.
Exactly. Don't give him a reason not to do the homework. Jerry, do.
Do you think that's because he's taking a photo of you?
Yes, I trust Jerry. Yes. Yes, Jerry.
It's time.
Yes. Oh no, Jerry, be nice. Let me just stop this video.